Let's understand kinetic theory of gases in this video. Have you ever wondered why gases store energy in different ways when they move or vibrate? And how we count those ways? Today we will break this down step by step in simple terms. First, degrees of freedom tell us the number of independent ways a molecule can move. A single atom in space can move along x, y, and z directions, so it has 3 degrees of freedom. For a diatomic molecule, besides those 3 translations, it can rotate in 2 more ways, and it can vibrate along the bond, so it gains more degrees of freedom. There is a general formula. Degrees of freedom equals 3 times A minus capital R, where A is the number of atoms and capital R is the number of independent relations. Using that, monoatomic gases give F equals 3. Diatomic gases often give F equals 5, and linear triatomic gases give F equals 7. Now the law of equipartition of energy says energy is shared equally among all these degrees of freedom when the system is in thermal equilibrium. Each quadratic degree of freedom gets 1/2 kT on average, where K is Boltzmann's constant and T is temperature. Vibrational motion has 2 quadratic parts, kinetic and potential. So it contributes 2 times 1/2 kT, that is kT. Let us see how this works for kinetic energy of a molecule moving in 3 directions. The kinetic energy has 3 parts: 1/2 mvx squared, 1/2 mvy squared, and 1/2 mvz squared. And their average values add up to 3/2 kT. For 1 mole of a monoatomic ideal gas, the internal energy becomes 3/2 RT, where R is the gas constant. From this we get molar specific heat at constant volume equals F divided by 2 multiplied by R, and at constant pressure equals quantity F divided by 2 plus 1 times R. This leads to simple values. For a monoatomic gas, Cv equals 3 divided by 2R and Cp equals 5 divided by 2R, so gamma equals 5 divided by 3. Let us now work a solved example. N moles of a diatomic gas at temperature T are heated, so T stays constant, but N moles convert into monoatomic gas. What is the change in total kinetic energy? Start with the initial kinetic energy for the converted part, written as 3 divided by 2 times N RT. After conversion, the final kinetic energy of that sample is 3 divided by 2 times 2N RT, because the form changes as stated in the question. Now subtract initial from final to get the change. 3N RT minus 3 divided by 2N RT equals 3 divided by 2 RT. So the change in kinetic energy is 3 divided by 2N RT. Next, another solved example for specific heat of a mixture. Question number 2 asks, 1 mole of monoatomic gas is mixed with 1 mole of diatomic gas. Find the molar specific heat at constant volume in calories. Use Cv monoatomic equals 3 divided by 2R and Cv diatomic equals 5 divided by 2R, then average them for equal moles. The average is quantity 3 divided by 2R plus 5 divided by 2R divided by 2, which simplifies to 2R. If we take R as 2 calories per mole per Kelvin in these units, 2R equals 4 calories. So the answer is 4 calories. So what do we learn from this? We learn that counting degrees of freedom lets us split energy equally, and that gives internal energy and specific heats by simple formulas. Let us quickly remember, each translational or rotational quadratic mode gets 1/2 kT. Vibrational gives kT, and Cv equals F divided by 2R. Also remember, mean free path is the average distance between collisions, and it increases with temperature and decreases with pressure or particle size. Brownian motion is the random jitter of tiny particles caused by unequal hits from surrounding molecules. Keep exploring these ideas with practice, and you will see many problems become straightforward. Keep studying gently, and if you want more worked examples, Do explore EduRev for clear notes and questions. You will find helpful practice there.